And, okay, I have everything set up here. So yeah, okay. So yeah, I'm happy to be here. So I'd like to thank the organizers for this opportunity. I'd like to thank everyone who's watching this here and online. So happy to be here. And my name is Luis Chavier. I'm a software developer at a Canadian company called Mission Control. And I'm the technical lead of the team that's building the Spaceflight AI deployment toolkit, which is what I will demonstrate here today. This is a set of software tools that we created to support running neural networks on embedded systems, and we focus on systems that are more flight oriented and lightweight, and especially the ones that contain an FPGA and a traditional processor on a single chip, usually a multi-core processor. And I'm going to talk more about that today. So yeah, just so I'll talk first about, I have a few slides. I'll talk about some of our mission contributions, and then I'll describe the application and the hardware that I'll use for the demo that I have here on this table. And then I'll talk about the software architecture of the toolkit and how it can be used to deploy things to space. And next I'll do a live demo. I won't code, but I will just run some commands and walk through some code, and that runs those neural networks, and then I'll compile and run it on the board. And let's see how it goes. So about our company, so we're focused on software for use in space, and we're based in Ottawa, and we have uh, rovers and robots where we test our software there. We even have like uh, uh, a lunar analog there where we test rovers, and we're contributing to a few missions, and I'm going to talk about two of them today that are related to this demo. And we work with several space agencies and companies and other institutions, and you can see some of them on this slide. So the first mission contribution I want to talk about is our lunar AI capability demonstration. So there's a Japanese company called iSpace that launched a lander to the moon in December last year. And we just learned on Tuesday that it entered lunar orbit. And it's scheduled now to land at the end of April on the moon. And it's carrying a rover called Rashid from the Mohammed bin Rashid Space Center in Dubai. And this rover will capture images from the lunar surface and send them to Earth through a data link with the iSpace lander. And we have a payload on that lander that will capture those images while they're being transferred, and it will process them on board using a neural network that we designed that we call MoonNet. A MoonNet is a convolutional neural network that does semantic segmentation, and it classifies each pixel of that image into one of 7 classes. Some examples are like rock or crater, lunar sky, rover track, a few other things. And the reason we're doing this on board is to demonstrate the capability to support onboard autonomy using this data and for future missions. So for example, we can imagine like rovers that can use this to drive themselves, or perhaps more autonomous scientific instruments. And yeah, I'd like to acknowledge that this work is supported by the Canadian Space Agency. The other example I want to mention is an experiment that we are running on the satellite created by the European Space Agency called OPSAT. So OPSAT is essentially a platform to run experiments in space in low Earth orbit, and you can register to be an experimenter with ESA and then run things on the satellite. So what we did is to use the deployment toolkit to run a neural network there, and what we did was to run a network that was created by ESA, and that's called SmartCam. Actually, the experiment where they used that model is called SmartCam. So we took that model, it's available online, and then we deployed it using our toolkit, and yeah, and we ran that. So yeah, what it does is it's an image classifier. So as you can see here on the bottom right, it classifies the images captured by the satellite into three classes. So we have Earth, Edge, and Bad. Bad is just bad. So things like whoever trained that network thought some images were not useful. That's what they trained the neural network for. So we just run that network, and the idea here is that you don't want to download like the images that are not useful. So you run this on board to avoid wasting any downlink with this. I think one important thing here is that we're running a model that's not ours. It's someone else developed, and we used our toolkit to deploy it into space. Okay, on to our application. So we run like what is a classic of deep learning. Usually, it's sort of the hello world of convolutional neural networks, at least for computer vision. And so we have a network architecture, and we'll train that using a labeled data set of handwritten digits, and that network would recognize those digits. I'm not going to do the training today because we don't have a lot of time. So I'll just do what you see here on the right, which is the downward arrows there. We'll be running on the platform, on the hardware here. So our software will load the trained neural network, and then it will process the images with handwritten digits and do a few predictions. So once it loaded the CNN, the model, it will load an image. It's a 28 by 28 pixel image with 8 bits of depth. It's just a grayscale image in the PNG format. And then the software converts that to an array of floating point numbers with single precision. And that's the input of our network. They're just numbers from 0 to 1, indicating the intensity of these pixels. And then our software runs that, does inference using that input and that network, and generates an array of predictions. So this is an array of 10 floating point numbers, again from 0 to 1, and each element refers to one digit. So index 0 is digit 0, index 1 is digit 1, and so on. And those are the predictions of the network. So the higher the value, the more the network thinks that that's the digit that was detected. So a little bit about the platform that we use. This is a development kit from Critical Link. It uses, I'm not going to talk about all the specs here, but the important thing is that it uses a Cyclone 5 system on chip. It's very similar to what's on the OPSAT satellite. And it has, the important thing here is that it has an integrated FPGA and a dual core ARM CPU. And it has some RAM on the Mighty SOM. We call it Mighty SOM. It's the blue thing that you see here. It has RAM and it runs Linux, and that's what we're going to use. Everything else is just the green board is just for connectivity here. So this is the software architecture of our toolkit. So the way it works is usually like there's a machine learning practitioner who have a network that they want to run, and then they will train that on a usually popular framework like PyTorch or TensorFlow. And this will be in a certain format, and each framework uses a different format. And what we do is to support an intermediate. It's not intermediate. It's like just another industry standard called NNEF. This was created by the Kronos group. It's a consortium, and it was created to facilitate interoperability between these systems. So, For example, the PyTorch, from PyTorch, you can generate an NNF model from pretty much any framework. So after you have the NNF model, I'm going to do that later in this presentation. And so we use the first element of our toolkit, which is the NNF compiler. So the NNF model is very high level. So what the compiler does is to break down those high-level operations into lower-level operations, and we end up with what we call a bytecode, which is it's kind of an executable program. It has instructions, it has data. For example, the weights of your neural network or model parameters, they are all contained into that bytecode. So that's one part. So usually you do this whenever you have a new model you need to recompile it using the compiler, and then when that's ready, you run that on the board or on our platform using our runtime environment, which is the second part of our network. Sorry, of our toolkit. So itself, it has two parts. So there's a library. It's written in C++, and it has bindings in C, but we're looking into supporting other languages too in the future. There's interest in other languages. And so basically, you can use this library to load the bytecode and run inference with using that network. You pass it an input, like an array, like I mentioned before, and it will give you an output. It does everything for you. You can run this only on the traditional CPU, or you can also have this optional FPGA support. So if you have a system on chip that has an FPGA and that we support with some additional FPGA logic and drivers, you can use that to run certain operations, and we focus on running the computationally intensive operations, which are, for this type of network, they're typically the convolutions. And yeah, we're essentially doing multiply add operations, a lot of them. And these are you can look at this as matrix multiplications or dot products, essentially. And with that, an important thing here is that you can offload your CPU, for example, to do other things. Okay, it's time for the live demo. Time. What could possibly go wrong? So, yeah, I have another slide here. So the first thing I'm going to do is to generate the bytecode. So I'm going to use the two things. So one is the NNF tools package from the Kronos group. It's open source, so it's just a tool to convert models. And then I'll use our NNF compiler. So I already have this digits.onyx file. So Onyx is a very popular format that can be natively exported by PyTorch. So we're using that. So I have the file already, and then I'm going to use NNF tools to convert that to an NNF model. And then I'm going to use our NNF compiler to generate the bytecode. And okay, let's do that. So can you see? Can everyone see like the screen here, or I can zoom in if people have trouble seeing it? All good? Okay. So I have two terminals here. Well, let me just see if everything's still working. It is. So I have two terminals. This is on my laptop. I have an SSH connection here to the Mighty SOM. And here I have some code. So I have the Onyx file here. And the first thing I'm going to do is to convert that to, I'm just copy and paste a few things here. I don't want to risk like making mistakes. I've done this before, so. Okay. So yeah, I'm on that folder. So you can see here, it's about 5 megabytes, this model. And I'm going to run this command. So this runs the NNF tools. You need to pass the input format, which in this case is Onyx. And then the output is NNF. And then the file, which is digit.onyx, and it will save the output on a folder called digits.nnef. Okay. Right. You see it showed up here. So let's take a quick look here at what it looks like. So this is a model. It's a very simple one, and it's fairly readable. So you can look at, this is a computational graph of the network. We have a few convolutional layers, activation layers here, and you can look at there's a spec on the NNF website about explaining all these commands. Yeah, and here we have also some variables referenced on the code, which are contain the weights of your or parameters of your network, and these are stored in these files here, .dat files, and that's what the model looks like. So the next thing is to run the NNF compiler to convert this into a bytecode. So let me get my next command. And I'm going to run it here. It's going to save the bytecode inside this digits folder here. And I'm going to talk about what's inside here soon. So DSC is our, what's going on? Oh, but okay. Yeah, so we have a digits.bc. Our compiler is called DSC. Let me just show you. You can run it from a terminal, and it takes like a model, and you say what the output file is, and that's pretty much it. It's very simple. So here's the digits.bc. We can take a look and see the size is pretty much the same. You see, it's almost 5 megabytes. Okay, and that's the first part. Now we have the digits, the bytecode. I'm going to talk about the runtime. So the way it works, like, is you have usually some C code that's going to link to our libraries. So typically, you know, like with any C program, you'll include some headers, and I'm going to show that. And then you link against some libraries, and then it will generate an application. In this case, this executable here on the right called digits. You might want to link this statically with a .a library or .so shared library. We support both options. And what that application does is to read the digits.bc with the model, and then read a PNG file and do the inference, and then show what the prediction is. So what I'm showing here is the CPU version. So as I mentioned before, you can use the CPU or use the CPU and the FPGA. So for the CPU, we're going to use here, you can see, yeah, it's using the CPU folder. So there's a library for the CPU. The interface with that library is the same. So if you want to use the FPGA, you just use a different version of the library, and the interface is pretty much the same. Your program doesn't change. I'm going to show that if I have time to do it. So here you can see, yeah, so there's another folder called Cyclone5 with a different version of the library. And now this version we need some device drivers loaded on the operating system, and some FPGA logic should be there too. And then the library will take care of just running things on the FPGA for you. So, yeah. Okay, so.
You have plenty of time.
Hmm?
You have plenty
of time. Okay. So next thing, let's see. I'm gonna compress this folder. Oh, let's take a look at the code, right? Of course. So this is the DSR is the name of it. It's the Deep Space Runtime. It's like we have a header here with you know, some. I'm not going to talk about all of the functions here, but there's C functions. I'm going to talk about some of them when we look at digits.c code. But yeah, it's just one file with a bunch of functions. Then we have this, the lib here has the libraries. So for example, this is the CPU version. We also have shared libraries. I'm just going to use these static ones today. And we have here the version for the Cyclone5 that uses the FPGA. We have a few images here. Let me show you the images that we're going to use. So we have A4, A5, and A9. And the third party is just some code. It's all self-contained here. I wanted to keep things simple. So this is code to decode PNG files. It's all in a single C file. I'll compile that together with the application. So, and the application is this, digits.c. So let's take a quick look. So it includes like the dsr.h, which is our header. But I'm going to go directly to the main, to the main function. So it accepts two arguments. So the first one is the file containing the bytecode. The next one is a PNG file we're going to use with the input. And then it creates a context with this DSR create. After we have the context, we decode the bytecode from a file. You can also read it from an array if you want, if you're reading it from the network or something. And then we read the image into this array of pixels. There's a read PNG function. I'm not going to go into details, but it just decodes the PNG and saves an array. And yeah, after that, we convert it to an array of floating point numbers, as I mentioned before, from 0 to 1. It's very simple. And next, we execute the network with DSR execute, and we pass in the context here where we loaded the bytecode. And that classifies the image, and it will save. We pass in the output buffer, and it saves the output on that buffer. And number of classes here is 10, and number of pixels 28 by 28. What else? Yeah, we print the output, and then we look at which one has the highest value, and with this argmax function, it just tells you what's the digit that was detected. Let's see if there's something else here I can talk about. Yeah. Oh, there's a device name here. This is, if you're using the FPGA, you need to open a device that connects you to the driver. So if you're using the CPU version, it just ignores it. But yeah. So this is a UIO device in our case. I can now run things. Okay. Let me look at the next command. So I'm going to compress this folder. I'm going to compile everything, all of this on the board, because I don't want to deal with cross-compilation stuff, and just to keep things simple. And I will run this. Let's just take a look. There's nothing here. There's just a setup folder with some setup code to load the drivers. So, sorry. I'm going to compress this. Okay. So if you look at the terminal here, you see it's here. I'm going to extract this. Yeah, this is just because the date is not set on the board. It's not the problem here for us. Yeah, sometimes it takes a while. So yeah, so here's the code. Now I'm going to compile. So the bytecode is here, the C code is here, and everything else that I mentioned. I'm going to run this. So let's just take a look at this GCC line here. So we're compiling the digits.c and all those third-party libraries. We're saving it into the digits executable. We're including the headers here for DSR, including the library, C++, and yeah, these are just things for the PNG library. So what's going on? Oh, yeah, of course. Thank you. Yeah, it takes a while. Okay. So, oops. So there's our executable. I'm going to now run it with, so yeah, it takes a bytecode. I'm going to pass in the bytecode of BC. I'm going to run it with the 4. So let's run it. So you can see it here that, yeah, some log messages. So what's important here is the classifier output. So you can see that we have a bunch of 9s for the index number 4, which is what we're looking for. And it detects it's a 4. And let's do it for the 5. Oops. Yeah. And the 9. Yeah, a bunch of 9s here. So that's good. That's it. If I have time, I think, yeah, I could do it for the FPGA too. I just need to change the library, but it doesn't really change much here. It just compiles things with the FPGA, and you'll have the same results. You do it really quickly. So let's do Cyclone 5, and I'll call it digits FPGA. We'll do the same thing here. The result is going to be the same because that's what we're looking for. You know, you have to trust me that it's using the FPGA on this one because the inference times are pretty much the same. But yeah, that's it. I think I can conclude. Yeah, please check out our other pre-recorded presentation from my colleague Becca, and there's a lot more information about what we do there, our missions, and stay tuned for our lunar landing. Perhaps I can talk about that later in another workshop. And we're interested in collaborating with people to run neural networks in space. So if you're interested, talk to us. And that's it. I'm ready for take questions if we have time for that.